I think we're good now to start off, Ryan. So thank you all for coming. I get this flipping up. If you, can we get some quiet, please? Thank you. Thank you everyone for coming. If you haven't scanned the QR code, please do it now. Um, we have a wonderful talk prepared today by Ryan. So without further ado, take it away. Cool.
Okay. So I've been doing an honors for the past few terms on operation called local complementation. I'll be sharing like one such thing I'm looking at, like a small subset of the problem. But I've been finding this part kind of like quite elegant in how the invariants operate. It's going to be referencing concepts from like both like graph theory and maths. So hopefully from whatever background you're from, like some part of the talk should make sense, if not all of it. So I'll get started. So local complementation happens at a vertex V, and the transformation that happens is you consider every pair of neighbors of V, and we toggle this edge, meaning that if this edge exists, we remove it, and if it doesn't exist, we add it. And we call this new graph G star V. So as an example, on the left, we have like the sum graph G, and the neighbors of D is A, B, and C. For every pair of neighbors, we're going to toggle the adjacency. So since A and B are connected, we remove that edge. And since A and C are disconnected, we add that edge. And so the new graph we get on the right is G star D. Obviously, this operation is like kind of simple, but the graph can change a lot on every step, especially if the neighborhood of a particular vertex is quite big. We have some nice properties that if you invert on the same vertex twice, you get back to the original graph. That should be easy to see.
Can you explain it?
Sure. So if you invert on a vertex, you toggle the edges. And if you invert on the same vertex again, you toggle the edges back. And so you should get back to the original graph. And so that's one simple property that you have of the graph. However, like in general, it doesn't behave very nicely. And the graphs that you can get can look quite different from your original graph. And it can be quite hard to tell whether you got that graph from the original graph or some other graph, or whether like it's not reachable from the original graph. You also have that the operation is not generally commutative. In particular, if UV is connected, then it matters what order you invert on the vertices. Inverting on U and then V is different from inverting on V and then U. And so this means that if we are trying to get to some graph, the order in which we do this sequence of vertex inversions really matters. And we're going to fix this problem in a second with another operation built on top of this. But first, some background. It's very vaguely related to this concept in quantum computing known as measurement-based quantum computing, where what you're trying to do is entangle some qubits, and this is going to be, represented by some graph state. And by measuring the results of some qubits, this is how you get it to do stuff. In particular, you have the correspondence that vertices of a graph are like the qubits in your quantum circuit. And when you entangle qubits, this is like adding edges to your graph. But importantly, if you put a locally equivalent graph, like a graph that you can get by a sequence of vertex inversions, instead of your original graph, the result of the computation is going to be the same. So in order to do fewer number of entanglements or like fewer number of preparations, it's the same as finding a locally equivalent graph with a small number of edges and using that as the preparation of your quantum circuit. And so roughly that's the goal of my project, that given a graph, I'm trying to find a locally equivalent graph with the least number of edges. But in general, it's kind of just studying what graphs you can get to by performing sequences of local complementations. Hello. So there's an operation called a pivot, and this operates on an edge. So if U and V are adjacent, so we have the edge UV, then we define pivoting on the edge UV as to be inverting on U and then V and then back on U again. And it's kind of surprising, but it is true that if you invert on UV and then U, it's the same as doing on VU and then V. And so it kind of makes sense to be inverting on an edge. And this slightly fixes the problem of commutativity. That you just invert on an edge and it doesn't matter which endpoint of the edge you do first. Hello. So we're going to be looking at the pivot operation for the rest of the talk. And in particular, the pivot operation in relation to the bipartite graphs. For more general graphs, like some invariants will still hold true. But this is just like the example where the invariant happens the nicest and is easy to explain. And like easier to get results from this type of graph. So it's kind of hard to imagine what happens when you invert on U and then V and then U again, because a lot of edges are changing. But what's actually happening is this. So in a bipartite graph, you have UV being an edge. So they're going to be in different sections of your bipartite graph. And the edges that you want to toggle are the ones going between the neighbors of U and the neighbors of V. So these are the edges that go between here. In particular, like if there is an edge that crosses between those two sets, you're going to delete them. And if there is a lack of an edge crossing between those two sets, you're going to add them. And then finally, you swap the labels of U and V. And that's what it means to be doing a pivot. So over here, NG of U is just my notation to say the neighborhood of U in the graph G. Like this is the graph G. And we're excluding the vertex V because the edges you want to toggle are like between these two sets, not the edge UV. So this is just to exclude the edge UV. Concretely, this is what happens. So say we have this graph on the left, and we're going to be using this graph for the rest of the presentation. If we do a pivot on the edge AD, can anyone tell me what graph you're going to get?
Someone wants to join out on whiteboard with one of
I think your name is someone.
Oh, really?
Hi, someone.
I put forward I'm not really sorry.
Oh, man.
It would have voted.
Could you go back to the previous slide?
Okay, sounds good.
Okay, more than she could.
Yeah.
Okay, I can try to.
Okay.
You try to throw them the right size if now it's equal to yeah, that's right.
Wow.
That's how it works.
Okay, so you have the edges for the labels. So A, you have what? Yes. And then all the edges like between the lots and goals.
Yeah. So then they so the neighbors of A is E, right?
the neighbors of B is D and C. One word first. Oh, shall I? It's gonna draw anything, but still. Okay. Sounds good. The real possible word. That's easy to one yeah. You won't try to get a crowd. It's a use the ones. We can so E and then so this also gets advantage.
Yeah, that's it. Yeah, that's it. So the way I think about it is like the neighbors of I is B and C, neighbors of D is D. So there's just like yeah, so we talk about those. Does it make sense to everyone? Thank you. So like the neighbors of A is B and C, and then the neighbors of D is E. So the things that get toggled are like the ones that go between the set BC and the set E. So like this one gets added and this one gets removed. And then you swap the two vertices. So this is what you get. Yeah. Okay, cool. Now on to the invariant. So I'm gonna be introducing some linear algebra. If you don't follow, you can just ask. I don't know if I'm gonna go too fast. Oh wait, not yet. So if you can get from one graph to another graph via a sequence of pivotings, like a sequence of these operations, then we're gonna say they're pivot equivalent. And this forms an equivalence class. Like you can group the graphs by like sets based on what they're equivalent to. So like maybe one class would contain like the graphs pivot equivalent to some particular graph, and like if that graph's not pivot equivalent to something else, that would be in a different set. And so they form like pivot equivalence classes.
Can you remind us why we know it's an equivalence relation?
Yeah, I guess like from a like once you A1 background, a Mat 101 background, if you know what a equivalence relation is, you can formally show that this is an equivalence relation by showing that it's symmetric. Like if you can get from a graph G to H via a sequence of pivots, you can reverse that sequence of pivots to get from H to G. It's transitive because if you're trying to get from G1 to G2 to G3 via a sequence of pivots, you just do the sequence of pivots from G1 to G2, and then the sequence of pivots from G2 to G3. And I think that's one other property of equivalence relation, but that should be quite easy to show that is true. Yeah, and so we can talk about the graphs being pivot equivalent and forming an equivalence class. Okay, so this is the invariant which we're going to be studying. We call for bar-type graph, we call this matrix the graphic presentation of it. It has rows and columns labeled by the vertices of the graph. Like usually they're just labeled like row 1, row 2, row 3, but we're going to call this like row A and column A and so on. And so the rows are labeled with the vertices from one partition. In this case, we're using the top partition. And the columns are labeled by all the vertices. In the actual values, it's going to be the closed neighborhood. Let me first explain that. So the closed neighborhood of A is the neighbors of A plus A itself. So the closed neighborhood of A is A, D, and E, right? And the vector encoding of that is the vector where you have ones at A, D, and E. And that's going to be row A. So we have row A here, where we have ones at A, D, and E, and zeros everywhere else. And so this matrix encodes the, in the rows of this matrix, it encodes the closed neighborhoods of the graph. Right. You can quite easily see how we can get from the graph to the matrix, and the matrix back to the graph. And the form that this matrix always has to take is that the beginning submatrix has to be the identity matrix, and the remaining values, like columns D, E, and F, are going to represent the edges, represent the adjacencies in this bipartite graph. And this will always be the case. So like whenever we have a graphic presentation of a graph, the graphic presentation of a graph is going to need this identity submatrix somewhere in this graph. And if it doesn't, then it is not a graphic presentation. The values here are 0 and 1, but in particular, they're like elements of the binary field. So if we add rows together, like 1 plus 1 equals 0. And so we're just doing like addition mod 2, or we're doing like XOR if you're from a compsci background. And so that's going to make sure everything always is 0 and 1, even when we're doing row addition and subtraction. Now we're going to look at the invariance of this. It's going to be quite elegant because there's a lot of things relating to how the rows relate to each other, which tells you about locally equivalent graphs. But then you look at the columns, and there's also a bunch of invariants about that, tell you about like the pivot equivalent graphs. So we're going to look at the rows first and introduce an idea of local sets. And in a second, we're going to see how this is going to be invariant under pivoting. So for vertex set X, we say that LG of X is the symmetric differences of the closed neighborhoods. So if X is simply a singleton set, like there's only one vertex in there, then LG of X is simply the closed neighborhood of that vertex. And if you have many closed neighborhoods in there, taking the symmetric difference means that you take the values which are in exactly one of the sets, but not both. So if this definition doesn't make sense, I'll go through an example in the next slide. But we call set local if it's a potential output from this function. So we call set local if it can be formed by the symmetric difference of some closed neighborhoods. And you may see where I'm going with this, because previously we defined the graphic presentation where the rows are like basically the closed neighborhoods. And then now we're defining this function L of G, which is the symmetric differences of closed neighborhoods. And in fact, actually I'll go over that later. Okay, so just as an example, I'll show why these two sets are local sets. So the first set is a local set because, as before, we know the closed neighborhood of A is A, D, and E. So if we simply input to this function A, like the set with the element A, then the closed neighborhood of that is going to be A, D, and E. So by doing that, we can simply show that the set A, D, and E is a local set. And A, B, and E, we can split up as the symmetric difference of A, D, and E, and B and D, like this. It's the symmetric difference of that because the element D occurs in both, so we don't take it, and the elements A, B, and E occur in exactly one. And these two sets are exactly the closed neighborhoods of the vertices A and B.
Cool. Any questions from anyone so far? Questions on someone? Otherwise, I'm going to shoot everyone. I think Lydia understands it.
Okay, wait.
Yeah.
Can you go back a few slides? Okay. So, can you explain what this is again?
Yeah, okay. So this refers to like the closed neighborhood.
Oh, okay.
And this operation is a symmetric difference.
So like square brackets are closed, right?
Yeah, it's like how in set notation you have like the open set and the closed set. The closed neighborhood is like the neighborhood including the vertex itself, which is why over here, like the closed neighborhood of A is like the neighbors of A, which is D and E, and A itself. Yeah. Cool. Yeah.
Just make a difference at all.
Oh yeah.
So like, if only a business speed, it would come back.
Oh, I guess you do it one at a time.
So if I would come back.
Yeah, it'll come back. Yeah.
Okay.
Yeah. So I guess another way of thinking about doing a bunch of symmetric differences is it occurs in like an odd number of these sets. Yeah. So if you haven't heard of symmetric differences, taking the XOR of these sets, that makes more sense to you. Okay. Cool. The row span of a matrix are the rows that you can get by adding some combinations of rows together. So, like the vector of all zeros is a potential vector you can get by adding none of the rows together. Or if you add like, if you take single rows, those are also in the row span. And we introduced this concept because, as I hinted at earlier, sets of vertices can correspond to binary vectors where we have ones and zeros based on whether it's in the vertex set or not. And when you take the symmetric differences of these vertex sets, it's the same as adding the binary vectors together, because if you add like 1 and 1 together, you get 0. In the same way, if an element is in both of your sets and you take the symmetric difference, it's not in it anymore. And so these two ideas are very analogous. And so this remark here relates, a local set to the graphic presentation of G. In particular, a set is local if it's like vector encoding, like when you turn into a vector, whether zeros and ones, whether that's a vector in the row span of G. Yeah.
How do you do a vector encoding of sets?
Oh yeah, good question. I guess I kind of glossed over that. For example, that's here. So if you have the set A, D, and E, then the vector encoding is this vector, because it's got a 1 here, here, and here, and then the rest are zeros. Yeah. So like vector encodings and vertex sets are like basically the same thing, but in different forms. Just different representations. Yeah. So this remark is true because the rows of the graphic presentation are exactly the closed neighborhoods. And then the sums of these rows are going to be in the row span, but the sums of these rows are exactly the symmetric differences, which is what's defined by the local set function. And so this would be a local set. Cool. Now, there's a theorem that we're going to prove that bipartite graphs are pivot equivalent if and only if they have the same row span. So a vector is in one of the row spans if and only if they're in the row span of the other one. And based on the previous remark, this actually refers to local sets as well. This is saying that they are pivot equivalent if and only if sets which are local sets in G are also local sets in H. And this is very useful as a theorem in general, because you can classify whether graphs are pivot equivalent. That's quite non-trivial, because as we saw before, graphs can change a lot after every step. To prove that the statement is true, we're going to show that it's true for one particular example of pivoting, and then it should be clear how to extend that to generally pivoting. And since the operation would hold for any general pivot, then after any sequence of pivots, then it will still hold true. So the particular pivot we're going to do is on AD as before. We know after pivoting on AD, we get to this graph, right, where you remove the edge CE and you add the edge BE. As before, we know the graphic presentation of the graph on the left is this. And to find the graphic presentation of the graph on the right, we require the identity matrix on the vertices D, B, and C. And that's because of the properties of the graphic presentation I described before. So B and C are already can look like part of identity matrix, but column D has all ones, and so we needed to have a 1, 0, 0 instead of a 1, 1, 1. So one way that we can transform the matrix on the left to try to fix this issue is to add the first row to the second and third row. And you can see how this is going to change the column D to 1, 0, 0, and it's not going to affect column B and C. And so, in fact, if we do that, we get this graph, this graphic presentation, and this is indeed the graphic presentation of the graph on the right. And you can check that if you want. You can see there is an identity matrix on D, B, and C, and we can also rearrange the columns to put D, B, and C at the front if you like. More generally, maybe it's obvious that, not obvious, but you can generalize what we did here to adding one row to a bunch of other rows whenever you're doing a pivot operation. Now, since adding rows to other rows is called an elementary row operation, this is going to preserve the row span. And so the row spans of the graphic presentations will be preserved after doing these row operations. And so we can see after doing one pivot, the row span will be preserved. And so after doing any number of pivots, the row span will also be preserved. And so graphs will be pivot equivalent if and only if the row spans are equal. Cool. The theorem can also be proved more generally for any graph, not restricted to bipartite graphs. We're not going to prove this here, but it follows a similar structure with a more complicated graphic presentation. Yeah, this is quite an important theorem in the study of pivot equivalent graphs and locally equivalent graphs. Okay, now we're going to look at, yeah?
Does being locally equivalent, like, is it similar to being
Pivot? Yeah, so that's a good question. Remember how a pivot is made up of a bunch of local complementations? So if a graph is pivot equivalent to something else, you can split each of the pivots into a bunch of local complementations. And so pivot equivalent graphs are locally equivalent. But the converse is not true. There are locally equivalent graphs which are not pivot equivalent. But they're still quite related in the study. Yeah.
I can see like the locally equivalent doesn't follow necessarily from my hard one because it can stop being bipartite.
Yeah.
But is it true that like for any set of local inversions on a bipartite graph, such that the resulting thing is also bipartite, you can find some edge, some pivots that could do the same thing?
Yeah, that is true. One way you can show that is should be possible to show just from this. Because like if it's locally equivalent and it's bipartite, you construct the graphic presentation. And then actually, yeah, that's a bit non-trivial to show. It is true though. Yeah, I think in particular the theorem is that pivot equivalent graphs are not, locally equivalent graphs are not generally pivot equivalent, but in the case of bipartite graphs, they are. So that's an example. Yeah. Cool, good questions. So now we're going to look at the columns and see that there's some invariance there as well. In fact, an invariant is kind of a reframing of the invariant on the rows, but it's going to tell us something slightly different about pivot equivalent bipartite graphs. We're going to start with a simple example. If G is a bipartite graph, and let's say there are n vertices in total, and there are k vertices on the left side and n minus k vertices on the right side, there's going to be at most this many pivot equivalent graphs. And this is bounded with the parameters both n and k. To see why this is the case, we can look at the graphic presentation of any pivot equivalent graph. And we know from before that because of the form of a graphic presentation, we're going to need an identity submatrix somewhere in this graphic presentation. So we can say the graphic presentation is on sum of the k out of the n rows. Sum of the k out of the n columns. And so there's n choose k ways to choose these columns. Next, once we've fixed where the identity matrix is, the rest of the graphic presentation is actually uniquely determined. One way we can see this is via the uniqueness of reduced row echelon form. It makes some part of the graph identity matrix if it can, and the rest of the matrix will be uniquely determined. You can also see it because the graphic presentation is like a full rank matrix. And so if you take some subset of columns and fix it, the other columns are going to be uniquely determined. If those two explanations don't make sense, don't worry. That's not going to affect the rest of the talk. This lemma is quite nice because it's otherwise quite hard to study how many pivot equivalent graphs you can get to. And in fact, we're going to see this lemma is a corollary of the invariant I'm about to introduce. To introduce this invariant, I'm first going to talk about matroids. So a matroid can be defined in terms of its bases. So a matroid is a pair where V is just some arbitrary set, like a set of labels. You can think like a vertex set contains the numbers like 1, 2, 3 or something, but that doesn't particularly mean anything. And subsets of these labels is going to be called a base, and then collections of subsets of these are going to be called the bases. So, yep. These bases need to satisfy two properties. The first property being that there's at least one base, so you can't have the an empty set as the collection of subsets. And the second property is called the exchange lemma. If you have two distinct bases, S and T, then there is some item in S that you can remove and some new item in T that you can add such that this new set is still a base. So I guess you like swap out some item and you swap in some new item from T, and the set is going to remain a base. And these are just, like for now, kind of arbitrary properties. But because this is a well-studied structure, by showing that these two properties are true, we can call whatever we have in Matroid, and then some nice known results will apply to whatever we're studying to. We call matroids equal if their bases are equal. So bases of a matroid are uniquely identified. Cool. As an example, let V be the set of integers from 1 to 7, and B, the bases, be the size 2 subsets of this. And we're going to show that VB is indeed a matroid by showing that it satisfies these two properties. Firstly, it will satisfy this first property because there's the base 6, 7, which is a base of this matroid. So there's like at least one base here. And the exchange property holds because if we take any subset of size 2, say we take 6, 7, we can remove like any element from it. Say remove 6 to get 7, and then add some elements from T. And because T is different from S, there will be a different element you can add. And so, by adding this, you're going to return to a set of size 2. And sets of size 2 are bases, so you're going to get a new base. Yeah. So the exchange property is going to hold. Does this make sense? Cool. Okay, for my particular case, we're going to define the matroid where V is the vertices of G. That should be quite self-explanatory. And B is the set of K vertices where the corresponding column vectors in the graphic presentation of G are independent. So remember that the column vectors there's for each vertex there's a corresponding column vector in the graphic presentation. And you're going to choose some subset of those which are linearly independent, and the size of that subset is going to be K. And if that's the case, then that's going to be a base of your matroid. Might be quite hard to understand, but there'll be an example in a sec. We're going to show that this is a matroid, and if it is, we're going to denote this as the matroid of G, like fancy M of G. So firstly, we need to show that it's not empty. So we need to show that there is at least one subset of K columns which are independent. So because the graphic presentation has this identity part, we can take those identity columns. There are going to be K columns there, and those columns are going to be independent because they form part of the identity matrix. And secondly, the exchange property is true because we can remove
There's free food coming.
Sorry, the noise is,
You can have my seat.
Do you need to order more food, Alex?
I will.
Okay, sounds good. Thank you.
Yes. Oh, it's full of my car. You know.
Secondly, the exchange property is true because if we take k columns and we remove any column, the rank is now going to be k minus 1. Like initially the rank was k because they're independent. Remove any vector, then the rank will be k minus 1. And then from T, because that has rank k, there's going to be some vector you can add to S in order to achieve rank k again. Then since you achieve rank k in this new set, then it's going to be independent. And so this is a new base. Okay. I don't have an example here. I'm going to go back here. For example, in the graph on the left, we have that the columns A, B, and C form a base because these three column vectors are linearly independent. That should be quite obvious. We have that B, C, and D form a base because these three column vectors are independent. Oh, and importantly, both those sets have size 3. Yeah. And so there's going to be a bunch of bases that can be seen in this graphic presentation, and a bunch of bases that can be seen in this graphic presentation. Cool. And so the theorem is that if these bases are equal, we call the matroids equal, and the matroids being equal happens exactly when the graphs are pivot equivalent. So this is also very cool. It's like looking at the columns and instead of looking at the rows and having an alternative way to determine if graphs are pivot equivalent. So yeah.
Wait, does that mean you only have to look at the linear independent columns?
Yeah. Yeah, like the linear independence of the columns is enough to tell you whether graphs are pivot equivalent, which is really crazy. I guess there could be a lot of bases, like there could be up to n choose k bases. But it's just that the structure given by the graphic presentation is so rich that there's so many things in there that tell you about pivot equivalence. Okay, we can see that this is true. Oh, what happened? Because we have the previous theorem where graphs are pivot equivalent if and only if their row spans are equal. And if row spans are equal, that means we can perform like elementary row operations. Hello. To get from one graphic presentation to another one. By performing elementary row operations, you preserve the independence of columns. This is because, like, I guess if you add two rows together, and if you consider two columns, you can kind of imagine that they stay linearly independent. I don't have a formal proof for this. So looking at the row span is like kind of equivalent to looking at the independence of the columns. Additionally, it's going to tell us more about pivot equivalent graphs. In particular, if we have some base of the matroid of G, then there is some pivot equivalent graph to G, where S is the vertex partition. So as before, we saw that B, C, and D was the base. That means there was a pivot equivalent graph to G, where B, C, and D form one side of the bipartition, and like A, C, and E form the other side of the bipartition. The way we can show this is by doing a sequence of like equivalent statements to get from the left-hand side statement to the right-hand side statement. So first, if S is a base of the matroid, then that means that the column vectors corresponding to S are independent. If they're independent, that means that you can perform row operations to change these k independent columns into an identity submatrix. And that's going to change the rest of the matrix, but we don't particularly care about that. Once we change these k columns into the identity submatrix, we can see that this is the graphic presentation, where that's one of the partitions. And so that happens exactly when a pivot equivalent graph of G has the partition of S and the remaining vertices B minus S. And so if you think about it, the lemma that we proved at the start of the column-wise section, we said like the number of pivot equivalent graphs is at most n choose k, comes from the fact that the number of bases of a matroid is at most n choose k. And each of these bases is going to correspond to exactly one pivot equivalent graph. Cool. So that's all the invariance. A bit about my research, not really much here, because it goes a lot more into technical things. But just a rough overview is that I'm studying minimizing edges, and the number of edges is very closely related to the number of ones in this matrix, because every one in this matrix corresponds to an edge, except like the identity submatrix part, which is going to ignore that. So in order to get a pivot equivalent bipartite graph with very few number of edges, is the same as finding a graphic presentation with a very few number of ones. And so that's basically what I have to study in linear algebra terms. And so the two things that I was looking at is finding a pivot equivalent graph with the least edges, is finding the sparsest basis of the graphic presentation with some restriction. And I show that this is NP hard. And then I show that there are like pivot equivalent graphs which are dense, and where every graph pivot equivalent to it is also dense. And this is kind of surprising, because you can imagine if you have some like really complex, really dense graph, you just do some pivots, and it might like add some more edges or delete some edges. But roughly, you should be able to do something to get the number of edges to be smaller, or to be at most half dense. But I show that it is possible for all the pivot equivalent graphs to be dense. Okay, as a summary of all the invariants of the graphic presentation, I guess I just find it really cool because the graphic presentation is basically just the adjacency matrix, right? But then there's all these like very cool facts that come out of it, and that are very related to the pivot operation. So like first we've defined the graphic presentation as having rows being the close neighborhoods of G. And then we realize that linear combinations of this row is simply a local set, where local set is the symmetric differences of some close neighborhoods. And then we realize that if L is a local set, then it's in the row span, which I guess kind of follows from the previous fact. This just means that local sets and being in the row span are very similar. But very surprisingly, very surprisingly, that the local sets are equal exactly when the graphs are pivot equivalents. And this gives us a nice way to look at pivot equivalence. And then looking at the columns, we like define the matroids as the independence columns with some restrictions, and show that this is also another way to determine the graphs of pivot equivalence. And then additionally to this, it tells us something that the rows don't, and it tells us when sets can be an independent in G. Hang on. It tells us when sets are a partition of some pivot equivalent graph. Overall, I guess even if some stuff didn't make sense, I hope the invariants make sense and you learn something about graph theory, linear algebra, or like about my honors presentation. Cool. Thank you.
Do you want to take questions now, Ryan?
Sure.
So we'll end the stream now. Thank you, Ryan.
Thank you.
Hope people have questions.